But I'll be talking to you today about using a microbial electrochemical separator for research we're doing in the lab for harvesting carboxylic acids from corn fermentation effluent stream. So corn ethanol is becoming a more important energy product for the U.S., especially with efforts by the government to mandate increases in ethanol production from 50 billion liters of ethanol in 2011 to actually 110 billion liters in about 5 or 6 years. And as part of making this ethanol, they actually ferment the corn, and you actually get basically 6 times more volume in this corn beer stream that's used to do the distillation to make this pure product of ethanol. And through doing distillation, you actually end up losing about 25% of your energy that's going into it in order to separate this ethanol to a pure product stream. So what we're proposing to do in the Engineering lab is to improve this product recovery from the energy on corn beer streams by converting this 15% ethanol stream into something with a higher purity, something that's easy to separate out and use much less energy. And the way that we're proposing to do that is to extract carbon from the ethanol that's in these streams using chain elongation to make carboxylates. And some of the properties that make this a very beneficial process is that the carboxylates have a very low solubility at certain properties, especially at low pHs, and it can basically be separated out through diffusion, which I'll show you some slides. But the process of chain elongation is done through reverse beta oxidation in bioreactors that we're running in the lab. And these reactors are run at 5 pH, and basically we take the ethanol that's produced that's in the corn beer stream, and it's converted to acetyl-CoA, and is run through cycles of chain elongation. And in our reactors, we're typically converting butyrate to caprate. So in our product streams, they end up getting a large fraction of caprate. But it's important to note that it does start with acetate and gets converted to butyrate, and then another chain elongation cycle happens and then converts butyrate to N-caprate. And we get a very nice, easy to separate product here. This is a recirculating line at the solubility of caprate, and we're actually getting phase separation there. And that's what makes this process very nice, is that with an electrochemical separator, we can get the concentration in a recirculating line to be at the solubility, and anything that ends up transferring through ends up getting physically separated out. And we use this this property here of at around high 4s and low 5 pH. You get a low solubility where this will happen. And in particular, we're interested in caprate of the carboxylates because there's already applications for them. They're used as chemical precursors for biofuels and pharmaceuticals. Farmers are interested in them as an additive into animal feeds, and they're also used as with interest for antimicrobial properties. Some research already published from the Engineering lab a couple of years ago. We were running, and actually still running, this bioreactor here. It's a 5-liter bioreactor run in semi-batch and operated at 5.5 pH and maintaining the pH with NaOH. And in the end, with this bioreactor and hollow fiber membrane added onto the effluent of it, we're able to produce 2 grams of caprate per liter per day. And basically upgrading the bioreactor concentration from around 50 millimolars of caprate to something much higher, around 500 millimolar. But still, even at this concentration, you don't get the phase separation. And it's important to note that this is in the caprate form, not caproic acid, which is what a lot of people are very interested in. So overall flow of how we added the electrochemical separator to the bioreactor is basically this is what was already in existence in the lab. We had the bioreactor running in recirculation, added on with the hollow fiber membrane, which is also recirculated, and the hollow fiber membrane before, this was our product line. This is this extraction solution. And basically what we did was just added the electrochemical separator onto the extraction solution and operated in recirculation to basically harvest out these carboxylates. It's important to talk about the separation process that's happening in this liquid-liquid separator. As I mentioned before, the concentration in the bioreactor was quite low compared to what we're getting out of the hollow fiber membrane. So the bioreactor was run at about 5.5 pH, and meaning that of the caproate species that are present, about only 25% of them are in the acid form. And what we did was ran this hollow fiber membrane, which is basically just two chambers with a membrane separating the two lines, and we filled this line with mineral oil with topo, which is a solvent that particularly increases selectivity for longer chain carbon. So it's able to collect more of the carboxylates. So you end up getting transfer of caproate through into the mineral oil, which is transferred through pumping into this second membrane, where we increase the pH so that we can increase the solubility in the extraction solution. And at this point, the pH is higher, so we actually have 0 caproic acid in there and high caproate. Now, the electrochemical separator is added onto that last hollow fiber membrane unit here, and it's just recirculated through the electrochemical separator. So the cathode chamber here is run at 9 pH, and the anode chamber, just through the reactions that are happening, is maintained at 2. It's a very simple architecture. It's 250 milliliters per chamber, anion exchange membrane separating the two chambers. The cathode electrode is stainless steel, and the anode is titanium with a iridium oxide coating on it. And running it in galvanostatic mode, we're able to get a very high diffusion of caproic acid through the electrochemical separator. And what's happening here is at this pH, we have a high solubility for caproate. And on the electrode, we're actually breaking down water into hydrogen and hydroxides. And on the anode side, we end up getting water breaking down to oxygen and hydrogen, which lowers the pH and basically allows caproate to transfer through and be formed caproic acid. And over time, after this reactor gets to steady state, any transfer through after it gets to max solubility ends up coming out as a pure product on the top, which ends up just dripping off. This is what the system actually looks like, so not exactly as in line as the last pictures I've shown you. But we have the bioreactor here with a lot of pumps doing recirculation, and we have the two hollow fiber membranes measuring gas, and basically so we have this hollow fiber membrane recirculating into the extraction solution, and the electrochemical separator basically feeds off of this, and we're harvesting the caproic acid off of here. And just a little zoom in picture, you can see very nice phase separation here, and we're able to just actually as more product comes through the carboxylic acid ends up just flowing off of the top and going into a collection bottle. And it's just a nice picture of the product that we make. We end up in the sizes of the reactor and separators that we have right now. We're getting about 5 grams per day, which is about 5 milliliters per day, and you can see it's a very nice, clean product. And just a little bit about some of the experiments that we've done on the system. We just wanted to try seeing if there's any bit of a higher flux in the reactor. So running in a galvanostatic mode, we doubled the current to see what would happen to the reactor, and you'll see extraction data in a minute. But basically, what I wanted to show here was that we were doing experiments, and there happened to be some oil that ended up transferring onto the membrane and basically clogging it. So we had to clean it out, and you'll see that basically the voltage came back to where it was before, and showing that the system is very robust. So we also measured pH. It's very important for keeping playing around with the solubilities and the transfer rates through the electrochemical separator. And you can see that even after that disturbance at the end of phase 2, the pH is very steady. And another thing to note is that After the system, basically the cathode got to steady state, we never had to add any base into the system to regulate the pH. So there's a charge balance in the electrochemical separator that ends up keeping everything very stable, and this is just less cost of having to add in any sodium hydroxide. So we're able to get a very high transfer rate of carboxylates, carboxylic acids through the electrochemical separator membrane and harvested. In comparison to the hollow fiber membrane that we had before, that was getting around 1 gram per meter squared day. In this system here, we're getting 500 times more. It's around 500 or 600 grams per meter squared day of carboxylic acid. And Coulombic efficiency right around 50-ish%. And just a final data point here. This is our product. We're basically getting a lot of very high selectivity for carboxylic acids, particularly caproic acid. We're only getting about 7% of other stuff. So about 93% is the target products that we're looking for. Running the system for a while, we've learned a lot about how to improve it for scale up and for longer term operation. One of them that we were seeing is that the potential poise across the electrodes actually increased over time. After taking the reactors apart a few times, we end up seeing a lot of oil films and biofilms accumulating on the membrane. So we're looking at methods to basically remove material that's accumulating on there and scaring off and cleaning the membrane. Additionally, there's a lot of opportunity to increase performance with new, better performing membrane materials. And also, we're looking at increasing the anodic anion concentration to increase transfer rates. And finally, we're also looking at removing that hollow fiber membrane setup to just run the bioreactor solely on the electrochemical separator. Before is 50 to 500, 500, and then to basically pure product here. So there's some work we have to do to make sure that we're not doing any feedback effects on the bioreactor. But this is basically the step that we want to go to be able to harvest off carboxylic acids from corn beer. So in conclusion, we've been able to operate an electrochemical separator that's capable of doing a very good job of doing product recovery on corn beer streams with a very simple operation and design for an electrochemical cell. We're getting high extraction rates at around 500 grams of caprate per meter squared day, and the product we're getting off is very high also. It's around 92%. And in conclusion, I'd just like to thank a lot of people in the Angenent lab, particularly J.J. Zhu, who can't be here. This is mostly his research, and Professor Angenent, and also our collaborators at Ghent University, Professor Rabai and Stephen Anderson. Yeah.
Nice job. Okay. Great. We have time for questions, please. Yes, speak loudly. Thank you. Can you tell me how to calculate the Coulomb?
Yeah. We take the current, and then we basically look at just the, just right here. We can basically look at just the charge of whatever is going to get acidified for the carboxylates. And then we just basically look at the product here and just calculate off of that and transfer rates.
Yeah, because the product is generated by electrochemical reaction.
But anything that comes off from the product is from the electrochemical. So basically, this anode chamber is at max solubility, so we're not getting any more accumulation there. So the only new product, and the only thing we see coming off of the reactor is whatever is electrochemically driven to leave from the cathode.